Hello. So today we are going to cover a topic called gray codes, and so there are some types of problems in programming interviews, in coding interviews that involves doing some sort of operation or some sort of answer on gray codes, and it's just a general good concept to know. And so gray codes are just a way to encode numbers, so that adjacent numbers have a single bit that they differ by. So let me just first cite some properties of gray codes. So one of them is that to be able basically to cycle through all 2 to the power of n combinations of n bit by changing only 1 bit at a time, right? Because each of them differ by only 1 bit. Another property is that basically a gray code number or integer differs by 1 bit with its successor in the encoding. So these two are the defining properties of gray codes. There are actually different types of gray code. And so, but in this today's video, we are going to look at only one type, which is the usual one that people mean when they say just gray code, which is reflected binary gray code. Now let's see how we can construct gray codes. And so the way you can construct them just by hand like this is that you start out from n equal to 1. So you would have 2 to the power of 1 combination, so just 2, and those would be just 0 and 1, right? And then what you do for n equal to 2 is just taking first these 2 numbers from the previous value, which is for n equal to 2, it's n equal to 1, and put them like this, and then reflect them like this. So the reflection or the reversing of these 2 above would be 1, 0, right? And then for the first part, we put 0 in front of it, and for the second part we put 1 in front of it, and so we would get the 2 to the power of 2 combinations, which are 0, 0, 0, 1, 1, 1, and 1, 0. And you can see 0, 0 differs by 1 with 0, 1 by 1 bit, 0, 1 differs by 1 bit, this one with this one, and 1, 1 differs by 1 bit with 1, 0. And you can see even it's cyclic also, because 1, 0 differs by 1 bit with 0, 0, right? And now let's see if you go to n equal to 3, just to really understand this. So what we need to do is do the same thing. So we need all the values from the previous n, and so 0, 1, 1, 1, 1, 0. And then we need to do the reflection of that. And so that would be basically 1, 0, 1, 1, 0, 1, and 0, 0. And then now we will put the values. So we will put 0 here in front of these, and then 1 in front of these. And now we got the gray code for n equal to 3. And we do the same thing every time. Basically, when we go to n equal to 4, we take all the binary representations of n equal to 3, and then do this reflection or reversing thing. And the top part we put zeros, and the second part we put ones in front, right? Okay, so if we try to write this just in a somehow like formal notation, not really formal, but just something to be easily to remember. So this basically here can be constructed recursively, right? So basically the binary reflected gray code that we are just talking about here can be defined recursively this way. So we know that the first value, which is the base case, which is when we have L1, which is n equal to 1, it's just 0 and 1, right? And Ln for the values, any n value, is just taking the zeros and putting them in front of the values for n minus 1 binary representation, and taking 1 and putting it in front of the values of the previous binary representation, reverse it, which is what we did here. We took 0, 1 and then reversed it to 1, 0, put 0 in front of them, of the non-reversed ones, and put 1 in front of the reversed ones. This notation here, I'm considering that basically when you do x dot L, I'm considering this means concatenation, and LR, by that I mean just L in reverse order, which is what we did in the example above. So a couple of properties to know about these gray code here. So the first one is that for any n here, the 2 to the power of n bit combinations that we have for each value n, each combination will appear only once in the list. It can be proven, but for now we just cite them here. And then 1 bit changes every time when going from one number to the next. That's the defining property that we talked about earlier. And also only 1 bit changes when cycling from the last bit to the first bit. Also, that's another property. Okay, so now let's look at how we can convert from gray to binary and how we can do the reverse. So here I just wrote down the binary representations of a couple of numbers. So here I'm doing it for n equal to 2. N equal to 4, so that's why you can see here 4 bits. And so we'd have 2 to the power of 4 combinations. And I didn't write the entire sequence, but you'll just get the idea. And so here we have the binary representation, which is for each number 0, 1, 2, 3, 4, 5. So just these values basically. And here is the equivalent, the gray code. How can you convert from that to the gray code? And so here I have A, B, C, D that represent just the bit at that position, just so that we can write a formula here. And then here for the gray code, same thing. And one thing we need to know, and you probably know this already, but just to reiterate, the XOR on binary XOR operation, which basically just if the bits are the same, the result is 0 if we XOR them. If the bits are different, then XORing them returns 1. And so, for example, 0 XOR 0 would give us 0, since they are the same bit. 1 XOR 1, they are the same bit, so that's 0, and 0 XOR 1, they are different, so that's 1. And 1 XOR 0, they are different, so that's 1. So that's something to keep in mind. And so to get so here we are doing the conversion bit by bit, right? So to get the bit at the same position for the gray code as the one in the first position here for the binary. So E here, which is this value, it's just A, so it's just the first bit in binary, it doesn't change. The second one, which is F, that's just A and B, that's just XORing these two values together. The third bit, which is G here, that's XORing the other two values, so this one and this one, right? So this one gives us A, XORing the 2 gives us gives us E, XORing the 2 gives us F, and XORing the two other, which are B and C, gives us J, which is this value here. And then for getting H, we XOR also the two successive values here, C and D. And you could apply this into these examples and you will see that it works. So for 0, 0, then our E is just 0 for the first value, and then XORing 0 and 0 for F, which is XORing A and B, that will give us 0. Same thing for G, we'll XOR 0 and 0, same thing for H. Now if we look at the second example, basically for E it would be 0, for F it would be XORing 0 and 0, so it's 0. For J it would be XORing 0 and 0 again, right? And so that would be 0, and for H it would be XORing 0 and 1, which would be 1, right? Now if we go to the third example here, E is still 0, and then F is XORing A and B, so it's XORing these two, so that's 0. And then G is XORing 0 and 1, so that's 1. They are different, so that's why we have 1 here. And H is XORing C and D, and so XORing 1 and 0, that's 1. So that's why we have 0, 1, 1. And you get the idea if you continue. Okay, so now let's see the reverse formula, which is basically going from the gray code here to the binary representation. And so the formula is just for A, the first bit of the binary, take the first bit of gray code. For B, the second bit of the binary representation, take the XOR of the two first bits of the gray code. For C, take the XOR of the 3 first bits of the gray code. And for D, take the XOR of the 4 bit. This of course generalizes to more than 4, but just we are taking 4 here. And so the idea is for the first, it's just the first. For the second, it's the XOR of all the values before. Every time it's the XOR of all the values before. And the last one is the XOR of all the bits from the gray code. So for example, A here is just the XOR of, is just E. B is the XOR of E and F. C is the XOR of E and F and G. D is the XOR of E, F, G, and H. And so if we take an example here, maybe take one like this one here. So to get the binary representation from 0, 1, 0, right? So this is E, F, G, and H. So for the binary, we are looking for the values A, B, C, D. And so A would be E first, right? And then B would be XORing E and F, which is XORing 0 and 1. They are different, so that's 1. C, which is XORing E, F, and G, so XORing 0, 1, and 1. So XORing 0 with 1, that's 1, because they are different. XORing 1 and 1, that's 0, because they are the same. And so here we have 0, right? Now for D, it's XORing E, F, G, and H. And so 0 XOR 1, that's 1. 1 XOR 1, that's 0. 0 XOR 0, that's 0. So the binary representation should be 0, 1, 0, which is exactly what we have here. Okay, so that's how we do the conversion on the bit by bit level from one to the other. Okay, so now let's just write the process that we did down so that we can derive the formula and understand it from this. So a couple of things we can notice here, right? So the first one is that the bit I at the position I of the gray code, right, this portion here, it's basically just, it's XORing the bit at position I in binary, right, with the bit to the left of it, right? To the left, or to the left of I. So, and if we are at the first position, like here for A, we just use 0, and so XORing 0 and 0 is always 0. So if we are here at the first position, we can just XOR by 0. And so this is basically what we did here. So every time we XOR the value at that position for the gray code, for the binary, with the value before it in the binary code, right? So for F, the position 1, if we start to count from 0, then we XOR these two together. So the value at the same position I and the one left to it. and then we go here, and for G we XOR B and C, so the value here and the one left to it. And for H we XOR D and the value left to it, right? So the bit I of the gray code is just XORing the bit at I in binary with the bit to the left of it. Another formulation some people use is that the bit I of the gray code is the parity of bit I and the bit to the left of I, which is just the same thing as XORing here. And for the first value, which is A, which here is 0, there is no value left to it, we can just use 0. Another thing we notice here is we can say what we did here for the binary, from gray to binary. So the bit I, so the bit I of a binary integer is the XORing of all bits at I and to the left of I, all of them, right? And to the left of I in the gray code representation, right? So that's what we did here when we converting from gray to binary. What we did is that the first value is E, and so we didn't do anything, right? So just left it at it. The second value, which is so this value here was just the first value. The second value is the XORing of the value at the same position, which is position 1, and all those left to it. Here it's the value at the same position and all of those left to it. And here, same thing, the value at position I and all of those left to it. Okay, so now we know we know exactly how to what we are doing here, and so let's just enumerate these and let's try to see the formula. So for one, for converting from binary basically to gray code. So there, what we are doing is just taking the gray code value is just, so the gray code value is just the binary representation, XOR the binary representation to shifted here. So the one left to it basically, that's what so this representation is just what we did here, which is XORing the bit at position I with the bit at the position left to it, right? So bit at I, bit left of I. So that's pretty much the formula for converting from binary to gray. Okay, so now let's see how can we generate a successive gray code numbers, basically a sequence of gray codes. So to do that, let's say we want to generate the sequence of gray codes for n equal to some number, right, for n. And so let's call it sequence here in Python, and let's say we get n as input. And so to generate this, it's very simple. We can just go for I in the range of from 0 of course to n, right? And then just do this formula here, right? Except b here is I, it's the number, right? And so we could just say, let's call this our result that will contain the sequence, and then we can just add I XOR I module shifted left by 1. Let's just write this more clearly. So I shift I 1, because I here would be from, let's say for n equal to 4, it would be 1, it would be first 0, 1, 2, 3, right? And we will get the binary representation of these and convert that using this formula basically to gray numbers. That way we'll get the sequences for n equal to 4. And that's pretty much it. Okay, so next I will be in another video. I will be solving a couple of Leetcode problems that handle gray code. If you want to stay tuned and watch those to get some practice in and understand this this concept. So thanks for watching and see you next time. Bye.